Thank you everyone for joining us this afternoon. I'm Alicia Newton and I'm the Director of Science and Communications at the Geological Society. And over the last year, we've been working with a group of societies all across Europe to work to create more opportunities for students to get involved in geology as a degree path, and especially young women and girls to choose geology. So as part of that, we're hosting this lovely Meet an Earth Scientist event today. And in this session, I'm so excited to have Ana with us. She is using fossil corals to study how the ocean has changed past thousands to millions of years. So Ana, thanks so much for being here. If you have any questions for her, just because we're recording this, we're going to use the Q&A function rather than allowing me to ask them out loud. So please, if you have a question as she's kind of telling you a bit about herself, please pop it in the Q&A box and we'll spend the rest of the session answering some questions. So thank you, Ana, please take it away.
Thank you very much. I'm gonna share my screen with you all so you can see the slides. I have prepared slides. I think you should be able to see my screen now. Excellent. Well, thank you everyone for being here, and thank you for the opportunity to be here talking to you about corals. So my name is Ana. I'm a coral scientist and a PhD student at Cardiff University. And currently I'm working on corals from Fiji. So in case you haven't noticed, I really like corals. Corals are extremely interesting for us, and I would like to talk to you about them, and hopefully you learn a little bit more about why they are so interesting. But everything has to be said. A few years ago, I didn't know absolutely anything about corals. I did environmental science for my undergrad in Spain, where I'm from. And back then, I had no interest for the sea. I didn't take any course on marine science or oceanography. The sea was something that was just very far away and not appealing whatsoever. So how did I end up as a coral scientist, you might ask? Well, what I was interested in was climate change, what is going on with Earth's climate and what is going to happen in the future. These are big questions that are asking ourselves as a society as we are facing the climate emergency at the moment. So as it turns out, to be able to understand the climate and what's going to happen in the future, we need to understand how it works. And for this, we need to look at past climate and how it evolved. That's what we call paleoclimate, the climate of the past. Cool. So we know that I was interested in climate and I went into paleoclimate. Where do corals come in? Well, in terms of climate dynamics, the oceans play a key role. They are a major carbon reservoir. They uptake carbon dioxide from the atmosphere. They are a major heat storage and transport system. So ocean and climate, they are intimately linked. Clues to the past climate and to the future change can be found in the ocean record. Ocean record, what it is, what do we mean when we talk about ocean record? That's how we find how the ocean was in the past. We investigate marine archives. Some archives might be the shells of forams, the shells of Bibles, or corals, among others. Corals is the archive that I chose. They are called archives because they record the environmental conditions in which they grow and they preserve them. So we can then go study them and extract that information from them, just as we use historical archives or archaeological archives to learn about ancient civilizations. We use marine archives to learn about the past ocean. So when I talk about corals, most people imagine tropical reefs with pristine waters and white sands. And yes, those reefs are built by massive corals that we use as archives. But these corals need very specific temperature and light conditions to survive. And that's why we only find them in tropical regions and shallow waters. However, they are not the only type of corals. If we go down deeper into the water column, we are going to find corals down to 3,000 to 4,000 meters, and way below that. They are known as deep sea corals, and they don't need sunlight to survive, and they can tolerate very cold waters. For this reason, this type of corals can be found all over the planet from pole to pole. So we have different type of corals in different type of regions, and we will study one or another depending on what we want to find out about the past ocean. They are just like pieces of a big jigsaw that is the past ocean. So how do we do that? We find out what we want to ask ourselves about the past ocean, and we need to go and collect the corals. So for example, let's say we want to study what was the deep ocean circulation 10,000 years ago. To be able to find out that, we will need to go into the deep ocean, that would be deep sea corals, and find out corals that were alive 10,000 years ago. How do we do that? Well, I'm going to show you. For that, we need ROVs or auto-submersibles or some sort of vehicle that allows to go deep into the sea. That's because they are so deep down that we cannot dive ourselves. So this one over here, you can see it has some cameras, some arms, and then some boxes in here. So we put everything on a ship and we go into the middle of the ocean. When we are in an area that we are interested in, we just deploy it, and eventually it will reach the ocean floor. It is connected to the ship, and we are from the ship driving it. So we get there and we find what is the ocean floor like, and we start looking for corals. Once we found the corals we need to collect them, and that's what we can see here. We found one coral over that rock. We want that coral to study it. So then we take the robotic arms, and this, just like a video game with a joystick, you pick up that coral and put it in a box and keep looking for more corals. So it's a high precision job, but it is extremely cool. Deep sea corals don't form reefs as the reefs that you are used to see in tropical regions. They form coral gardens, but they are still extremely beautiful. And chances are you are the first human being that are seeing that piece of ocean floor when you are there. So it is proper ocean exploration, and I think it's one of the coolest things I have ever done. This footage is from an expedition we did with the Icy Lab project on the Labrador Sea west of Greenland, and it was just very, very cool. Excellent. So that's for deep sea. If we wanted to study, for example, what was the variability of the monsoon 500 years ago or 1,000 years ago, then we would need to go and study shallow tropical reefs. And we would need to get there and collect some of the corals. How do we do that? Well, we literally need to jump into the water. This is some footage on an expedition in Fiji from Cindy Associan and Eleanor John. They are my supervisors at Cardiff University. So you go there, you put on your scuba gear, and you find a coral head that is big enough and healthy enough. And because they are very big, we cannot take the whole colony, the whole coral, back to the lab with us. So what we have to do is just take a piece of it. We literally drill a cylinder of coral material, is what we can see there, and that's the piece that we take with us. So this is footage with a pneumatic drill. We take a cylinder called coral core, and then the coral head remains on the reef, and we take our piece of coral with us to the lab. That's the coral core that we take with us, and that's the hole that we leave on the coral head. And then we need to make sure that we cover it with a cement plug, just so other organisms don't get inside the coral and get infected and transmit some disease. Right, so where were we? We decided that there was a question about the past ocean. We wanted to ask whether it was deep ocean circulation or was tropical climate in tropical regions. We went there, we collected our corals. We have our corals now in the lab with us. How do we extract the information? We are interested in how do we read these corals that we collected. Right, so deep sea corals and tropical corals or shallow water corals, they are somewhat similar in terms that they both build a skeleton out of calcium carbonate. It can be calcite or aragonite, depending on the species, and it is basically limestone. They build a rocky, stony skeleton. The information that we are after about the past ocean is within this skeletal material. We are interested in the skeleton of the corals. And why can we find environmental information in the skeleton? How is it that corals can record that environmental information in which they grow in their skeleton? Well, that's because some corals, as they grow in bands, just like tree rings. And just as we can extract some climatic information from the tree rings, we can extract some environmental information from the skeleton of the corals as well. So that's what we see here. The purple bit is the polyp, is the living part of the coral. It's pretty much like a jellyfish, has some tentacles and just for defense and feeding. And every season or every year, as they grow upwards, they build a new layer of a skeleton. This layer of a skeleton will be larger or shorter or more dense or less dense, depending on the environmental conditions. Let's say, for example, 1 year is warmer than usual, the coral might grow faster, and then we'll have a bigger band and less dense. But if it's too hot, it might stop growing whatsoever and will have no growth or a very thin and very high density growth. It depends. That's how we can read the physical properties of the coral skeleton. And if we go one step further, we not only look at the physical characteristic of the skeleton, but we look at the chemical composition of this rocky material, because corals that build their skeleton out of seawater, they get chemical elements from seawater, might be calcium and carbonate that is dissolved, and they combine them to form this mineral called aragonite or calcite. And along with these elements, they also introduce different elements like strontium or barium. And we can measure how much of these elements are there in the skeleton, and then we can understand what was the temperature back in time. If there is more or less strontium, that means that the temperature would be higher or lower. Or if we have more or less boron isotopes, we can guess what was the pH or the alkalinity of the water. We can measure, I don't know, carbon or nitrogen isotopes, more or less, would tell us if the productivity was higher or lower, if there was a lot of nutrients in the water, or if there were no nutrients, pollutants. There's a range of environmental information that is within these coral skeletons. And how much information of how deep in time can we go with corals? Well, that's going to depend as well. Most corals have a lifespan of 100 years. However, some deep sea corals have been found to be able to live up for 3,000–4,000 years, which is, it's mind-blowing. But that means that with one single coral, we're going to be able to extract loads of environmental information from hundreds and hundreds of years. That means that if we get a coral, collect a coral that was alive today and has lived for 500 years, we can measure ocean temperature, ocean salinity, nutrients up to 500 years back in time. But because this information is within their stony skeleton, is within the skeleton, once they die, they get preserved as fossils, and they get preserved for thousands and thousands of years. So we are able to reconstruct environmental conditions up to 100 years, 100,000 years in the past, which is, it is an enormous amount of time, and it is extraordinary. And yeah, corals, they are just extraordinary. So how do we extract this information? We know they record this information. We know this information is in their skeleton. We collected the corals. Now, how do we read it? What does it mean? What I have here is 3 images of one of the coral cores that we showed before were collected in Fiji in a tropical reef, and it's just the core split half in open. And it's a picture under normal light, a picture under UV light, and an X-ray from CT scans, like the ones you get when you go to the hospital. What we can see is that the growth bands that we were talking before, they become visible. And because we can see them, we can just count down from the time where the coral was collected. So this one in particular, collected in 2017, we can count 1 year below is a band below. We see a very dark area here, high density area here. So we can ask ourselves, that's 2016, 1 year below. What happened then? Well, in Fiji happened to be a bleaching event, and there was a very strong tropical cyclone named Winston, which caused several damage on the islands, several flooding, and that can be reflected on the coral skeleton. And like that, we can go down hundreds and hundreds of years. Once we know what year corresponds one section of the skeleton, like for example, we count down and we know that this area here corresponds to 2012, we can collect a bit of that skeleton, put it on a Mars spectrometer, which are machines that are so extremely sensitive that they can measure very, very small amounts of different elements, and we can extract information from, as we were saying before, barium, strontium, lithium, boron, carbon isotopes, oxygen isotopes, and that will give us information on temperature, salinity, pH, sea level changes, ocean circulation, and a whole wealth of information just from one single piece of coral. So just to resume, the past is key to the future. If we want to understand the climate, if we want to predict what the future climate is going to look like, we need to understand the past. And corals contains information on past ocean temperature, salinity, nutrient distribution, pollutants, sea level, etc. They are incredibly valuable for paleoclimate scientists, and that's why we study them. And that's all from me. Thank you very much. If you would like to know something else, just I have my contact details. Just drop me a message, and I'll be more than happy to pass you on more resources or more information.
Great, thank you so much.
Thank you.
One question already, and that's actually about, do submarine volcanoes affect any sort of coral reefs? And is there any way to possibly reconstruct gases emitted or understand the history of eruptions underwater?
Yeah, most definitely. Whatever is going on in the environment surrounding this coral is going to be reflected. Submarine volcanoes might change the temperature of the water, might change the alkalinity of the water, and that's going to be reflected. And we can measure that, and we can time when there has been volcanic eruptions, whether they're submarine or not. All this type of information is contained within the corals.
Excellent, thanks. I think hopefully we'll get a few more questions in, but my question is, what attracted you to this field, and why did you choose to go into geology as a degree?
That's a very good question. I'm not sure I have a clear answer for that. I guess that I've always been very curious about the environment, about nature, about different processes happening. And I guess once I knew I wanted to go to university and do a further degree, I did environmental sciences, but I wasn't sure if I wanted to do environmental sciences or geography or geology. So I just wanted to know more about the environment, and that's what drove me.
Great, thanks. So we've got another question, and that's, what is the most interesting or unexpected thing you have learned about the past?
Ooh, that is a difficult question. I'm not sure would be the most interesting. I would say definitely unexpected for me would be that when I started working on Fijian corals, well, I was just kind of expecting the corals to be decreasing their resilience, because on the last 100 years, seawater temperature has been constantly increasing. And what I found is that most Fijian corals were very happily with this temperature increasing, and they were just growing faster and faster, which is good news. However, that's not widespread. That's not always the case. It really is very site specific. But yeah, it's something I was not expecting.
Great. Is it possible to identify events recorded in the coral that are global rather than regional?
Most definitely. Something comes to mind, for example, lots of people use corals to study El Nino, Southern Oscillation. That's a climatic global event that's like in the Pacific Ocean and in the atmosphere over the Pacific Ocean. The currents just change in strength, change in direction, everything changes in order, and it affects both Asia, South America, North America. So yeah, that's a global event, and that can be recorded on the corals. So obviously corals are very regional, but there are some changes that, although they can be detected regionally, that is a global change. And we just need to learn from different pieces, from different regions, to understand how regional effects are part of a global effect, if that makes sense.
Yeah, that's great. Thanks so much. So we still have time for a few more questions if anyone wants to post them. I guess for me, it's what do you enjoy most about the work you're doing right now?
I think that my favorite part is always the field work. I just really like field work. I love going out, getting into the field and collecting the corals, seeing them. It's just a very cool feeling. So that's one thing that I really enjoy. But besides that, I really, really enjoy that part when you first get a batch of data after analyzing your corals, and you are the first person ever in seeing that data, and you are the first person ever in trying to find out what's going on with that coral and what it means and what is going on. And that's a very cool feeling. Maybe it's because I'm a nerd and I like science and corals, but being able to see the data for the very first time, it is a very good feeling.
Great. So now, do you find the same species of coral now and in the fossil record?
Yes and no. It depends how deep we go in the fossil record. If we go from a few thousand years back, 10, 20, 30,000 years back, we have similar species. If we go further deep down in time, they are somewhat different. But although they are different species, they are very similar to what we have today. And in a sense, they all build as carbonate skeleton, which is what we are interested in.
Great. And this is about why did you move away from working solely, I guess, in this environmental element or the environmental science?
Ooh, difficult. I guess because I like it. I like to do research, and when you get into research, you need to specialize in a very niche, in a very concrete thing. It is hard to do research in a multidisciplinary area, being able to cover a lot of topics. You're focused on one. You collaborate with people with different areas, and that's what makes a good science. But when doing research, mostly, and me personally, it is so hard that you need to focus in one topic, in one theme, and go for it.
Great. And here's a good question. So I absolutely love biology and geography, but I'm worried I have to drop one for the other. How much does geology and biology overlap within your degree?
Right. Well, because I did environmental science, I think environmental science, or at least the program I did in my university, it was a bit of jack of all trades. We had a bit of geology, we had a bit of biology, a bit of ecology, a bit of economy. So it was a multidisciplinary program. I think that if you like both, you can find programs that have bits of both. You don't have to go into one or another. And even if you go to one to another, and then further you want to change to a somewhat different field, if you start biology but then want to go into earth sciences or geology, it can be done, because the field is so multidisciplinary that although you choose one doesn't mean that you're going to end up in that field forever. You can jump from one to another, and the knowledge you learn, you're going to have that with you.
Yeah, maybe I can add a little from my experience. So I did something similar where I did a geology degree, but then ended up studying fossils as well. And yeah, I like to think of earth science as just applied physics, chemistry, and biology, in that you're taking that and applying it specifically to the Earth. So yeah, you can overlap many disciplines with geology quite easily.
Mm-hmm.
And as someone else, ooh, this is a tough one. Would you suggest a geography or environmental degree? Because I love them both.
Geez, I don't really know myself. I guess I would say environmental degree, because it's what I did. So in my experience, I learned a lot, and a lot of things I learned were very useful, but I'm sure a geography program would be equally useful. I think what I recommend is to have a look at those programs in the universities that you wanna go and see what they look like, because sometimes might have geography that is more from the social and human side, or some more from the physical or environmental side. But wow, that's a difficult question. If I had to choose again what to do, geography or environmental sciences, I would be in the same situation that I don't know what to do.
I think the nice thing too, and I'll do a little plug here for the Geological Society's website, is you can go and look at our careers pathways finder, and I think you'll find that geography and environmental degrees and geology degrees can lead you to very similar or some of the same jobs. And it just might be slightly different specifications depending how much you want to go down like an engineering route or a more contaminated land or sustainability route. So definitely check out our website and check out the degrees. And I think we're actually about out of time. So with that shameless plug for the website, I would like to thank again, Anna. Thank you for joining us.
Thank you so much for having me.
Thank you, thanks. And everyone, thank you for coming, and email Anna your questions or get in touch with the Geological Society. And I hope to see you again at some other events, either today or later on in the year. So thank you, everyone.
Bye.
Bye, thanks.